This is an introduction to systems and phase plane analysis, and in this video we will be talking about interconnected fluid tanks. So let's take a look at this diagram here and this problem we have here. We have two large tanks, A and B, and each tank is holding 24 liters of brine solution. Now they are interconnected by these pipes shown here. So fresh water, so this is going to be fresh water, flows into tank A. And let me just go ahead and highlight this tank. So this is tank A and this is tank B. At a rate of 6 liters per minute. And also 8 liters per minute of fluid are pumped in this upper pipe from tank A to tank B. And then we have 2 liters per minute fluid being pumped from tank B to tank A. And then finally we have 6 liters per minute leaving tank B. Now, we do see that the liquids inside each tank are kept very well stirred, so the mixture is homogeneous, and we have an initial brine solution here in tank A to have X naught kilograms of salt, and of course tank B has Y naught kilograms of salt. Now, what is our goal? Our goal here is to find the mass of salt in each tank at time t greater than 0. So we're looking for a formula for both x of t and y of t. We will be focusing on one tank at a time. And let's keep in mind that the rate of change of salt mass in each tank is going to be our input rate minus our output rate. Okay, so let's take a look at each tank at a time. So the first thing we need to know is that salt concentration, the salt concentration in tank A is x of t divided by 24, and that's going to be kilograms per liter, okay? And the salt concentration here in tank B is going to be Y divided by 24 kilograms per liter. We can do Y of t there. We also want to make note that the concentration or the rate at which this upper pipe carries salt out of tank A is 8x divided by 24 kilograms per liter. So that is leaving tank A. And then this lower pipe is bringing salt into tank A at 2y of t divided by 24 kilograms per minute. This should have been minute here. Okay, so let's look at the rate of change of the mass of salt in tank A. So in tank A, we're going to have dx dt is equal to, so we have 2 over 24y minus 8 over 24x. So you can see here that we have 2 over 24y going into the tank, and then we have 8x over 24 leaving tank A. So that's really, really important. And so we can actually simplify dx dt as 1/12 y minus 1/3 x. Let's do the same for tank B. And here we have dy dt is equal to, now as you can see we have 8 right here, 8x over 24. And let me put that x out in front like 8 over 24. X coming in, and then what we have going out is minus 2 over 24y. You can see that right here or right here. And then we have to think about the fluid leaving tank B, and that would be minus 6 over 24y. And we can simplify that. So we have dy dt is equal to 1/3 x minus 1/3 y. Okay, so the interconnected tanks are governed by a system of differential equations. And let's write those out. So we have x prime is equal to negative 1/3 x plus 1/12 y. And we have y prime is equal to 1/3 x minus 1/3 y. So as you can see, let's solve this second equation for x. So we have 1/3 x is equal to y prime plus 1/3 y. And so we come up with x is equal to 3y prime plus y. Now we can substitute this into the first equation. So we can bring this down, and we have x prime is equal to negative 1/3 multiplied by 3y prime plus y plus 1/12 y, and replacing x prime with 3y prime plus y prime. And why don't we go ahead and distribute that? So we will have a negative y prime minus 1/3 y plus 1/12 y. And then we will have 3y double prime plus y prime is equal to the opposite of y prime minus, and we can go ahead and make that a plus because we can combine these two. Actually, that would be a minus, and that would be 1/4 y, combining these two terms. Okay, so now we can write 3y double prime plus 2y prime, bringing this term over, plus 1/4 y is equal to 0. So now we have a linear second order dE with constant coefficients. Let's go ahead and write our auxiliary equation. So we have 3r squared plus 2r plus 1/4 is equal to 0. And let's go ahead and multiply every term by 4. And now, as you can see, we have, move that over there, 6 and a 2. Whoops, 2r. So we have 2r plus 1 and 6r plus 1 is equal to 0. That's really messy. Let's see. That's 6 over 2r, and that's 1/12, and that's 1 over 2r. There we go. Okay, and so we have r1 is equal to negative 1/2, and r2 is negative 1/6. So that general solution to that homogeneous equation, y of t is equal to c1 e to the negative t over 2 plus c2 e to the negative t over 6. Now, we found y, so we can use our equation that we found for x of t right here. So we will use that. X is equal to 3y prime plus y. We have that x of t is equal to 3 multiplied by y prime. So we can go ahead and write y prime of t here. And of course we have negative 1/2 c1 e to the negative t over 2 plus, and that's going to be a minus 1/6 c2 e to the negative t over 6. So we'll go ahead and place that here. And for y prime, negative 1/2 c1 e to the negative t over 2 minus 1/6 c2 e to the negative t over 6. Now we still have to add y. And so we have y of t shown there, c1 e to the negative t over 2 plus c2 e to the negative t over 6. So if we simplify all of this, we will come up with a negative 1/2 c1 e to the negative t over 2 plus 1/2 c2 e to the negative t over 6. And you can see where we combined our c1 terms, bringing that 3 in, and then our terms with c2. Okay. So now we have two undetermined parameters, C1 and C2. We will use our initial conditions to find those. So here we have x of 0 is equal to, and we have negative 1/2 C1, of course, because that t is going to be equal to 0, plus 1/2 c2, and that's going to be equal to x naught. And let's do the same for y of 0. We're going to go ahead and have c1 plus c2 so we can go ahead and solve these. We can come up with C1 is equal to, and we have to have y naught here. So going ahead and using that equation, we see that C1 is y naught minus C2. So now let's go to this equation, and we can see that x naught is equal to negative 1/2 multiplied by y naught minus C2 plus 1/2 C2. So x naught is equal to negative 1/2 y naught plus 1/2 C2 plus 1/2 C2. And we can see here that we have C2 minus 1/2 y naught. And let's go ahead and use a rational expression for that. So we have 2C2 minus y naught all over 2. And that is what x naught is equal to. Whoops, I meant to solve that for C2, what we were looking for, our constant. So C2 is equal to x naught plus 1/2 y naught. And again, we'll go ahead and have our common denominator, and have 2x naught plus y naught over 2. And that's what C2 is equal to. Now, we're going to go ahead and use that C2 and go back into this C1 equation. And we have C1 is equal to y naught minus, and this is our C2. So now we have that C1 is equal to, let's go ahead and have 2y naught minus 2x naught minus y naught. So C1 is equal to y naught minus 2x naught all over 2. So now we have our two constants, C1 and C2. And so the mass of salt in tanks A and B at time t are x of t, which is equal to, and we're going to go ahead and use our equation right here for x of t. So we have negative 1/2 C1. Let me go ahead and just write that out. C1 e to the negative t over 2 plus 1/2 C2 e to the negative t over 6. So this way we can have all of this together. Negative 1/2 y naught minus 2x naught all over 2 e to the negative t over 2 plus 1/2 and now we'll have our C2, which is 2x naught plus y naught over 2 multiplied by e to the negative t over 6. Let's go ahead and bring our final form for x of t. We'll bring that 2 into our expression so we can have the opposite of y naught minus 2x naught all over 4 e to the negative t over 2 plus 2x naught plus y naught all over 4 e to the negative t over 6. Okay, let's do the same for y of t. So we have y of t is equal to C1 e to the negative t over 2 plus C2 e to the negative t over 6. So let's go ahead and put our constants in. So we have y of t is equal to y naught minus 2x naught all over 2 multiplied by e to the negative t over 2 plus, and our second constant, C2 y naught plus 2x naught all over 2 e to the negative t over 6. I did want to add something that is, of course, consistent with what we would think would happen with our tanks over time. So over time, with fresh water entering the tank, eventually the salt concentration would be, or the amount of salt, the mass of salt in each tank will approach 0. So let's just take a look, or at least write this down. We note, and it is obvious, that the limit as t approaches infinity of, let's do x of t first, and so that's tank A, is equal to the limit as t approaches well, let's just go ahead and write 0. And you can see that here, placing an infinity here. Of course, then we have x of t will be 0 as t approaches infinity, and that the limit as t approaches infinity of y of t is also equal to 0. And that concludes this video.